All right, hello everybody. Today we are going to move on to composite sections. So I'm going to start off with a quick review, refresh our memory before we move forward. What we talked about last time was a stress due to a bending moment on a beam, and we said we have a strain profile shown here where we have, this is with a positive moment. I don't know why I don't have that in there, but if I had some kind of positive moment, then I know that on the top I'd have a compressive stress or a compressive strain, and on the bottom I'd have a tensile strain. I have this neutral axis halfway in between, if it's a symmetric section anyways. And I said that stress is related to strain linearly, so we can actually derive this equation saying sigma is equal to mc over I. So once again, a linear shape from top to bottom going right through this neutral axis. In general, we could call it my over I if I'm not using the outside fiber with the C's. So today we are moving on to a composite beam, a beam made of at least two materials. In this example, I'm going to have two materials where I can see that I have material 1 drawn in black is sandwiched onto material 2, and I have this uniform load W on top. And I'm saying on the side my E1 is greater than my E2. Now typically you'll know your materials, but we're saying we don't necessarily know, but we do know a relationship between our modulus of elasticity, so we do know which one is a stiffer material, E1 being stiffer. So if I were to look at a cross section of this, what this whole thing would look like is, this is like my shape 1, and then my shape 2, I'll keep the color so we can kind of tell what it looks like, is drawn in green. Should make them the same length, right? Something like that. This is 2, and this is 1. And I'm going to give you some dimensions here. We're going to call this B1, as in the width of shape 1. This is going to be B2, which is the shape, the width of B2. Of course, you can see that they're the same, but we do need to label them something different because that will be changing. And similarly, I have a height 1 and a height 2. Now here's the interesting part. Because shape 1 is stiffer, my neutral axis, even though it's symmetric, will not be through the center. Maybe you can picture this. If 2 were made out of like, I don't know, something like a foam, and 1 was made out of concrete, the foam wouldn't do anything, and it would be right in the middle of shape 1. So what I would end up with is a neutral axis that's going to be somewhere up here. I don't know where it is yet. That's part of today, is finding out where it is. But this neutral axis, if I think about what's going on with this neutral axis in my strain, what I would see is that my strain ends up being slightly skewed, where I have much greater strain on the top half than I do the bottom half. And once again, it's linear from one to the other. But I can see that, and this would have to make sense, right? Because if you think about the shape 2 being much less stiff, then as I apply this moment, it's going to stretch out much more, and I have this strain in tension that is definitely pulling out much more than this strain in compression. If I were to do the same thing and look at my stress, well, we know that our sigma, our stress and strain, are related by the fact that we have our modulus elasticity times our strain for our stress. So if I look at that, now I have a changing E value. I have an E1 and an E2, right? And because I have this changing value, what I end up with is this discontinuity, and I'd have something that kind of looks like this. So I go along, I still go through this neutral axis just like I did before, but then I get to this intersection between these two materials. So you can see I'm just kind of mapping over this line. When that happens, I have this point of discontinuity, and it comes into something, and then it goes, well, it's probably much less steep line. Don't know why that wanted to highlight, but having all sorts of surface issues as usual. So I end up with a stress profile that is nonlinear and has this kind of discontinuity right about there at the intersection. And the way that I deal with this discontinuity is I'm going to, it makes it really hard to analyze. and I can't analyze it because it's no longer linear, and we really like linear things. So we're going to come up with this new way to analyze this type of loading, or this type of composite beam, and this method is called the transformed area method. So with this transformed area method, in essence, what we're going to do with our example above is we are going to hypothetically change the cross-sectional area of shape 1 until we would in essence have the same effect of our Young's modulus, modulus elasticity. I want my two E's to be the same. So if I wanted to, in order to get these E values to work out, if I wanted to change E2 so to be equivalent to E1, I would have to do something like this, and this may make sense to you, and it may seem a little confusing, but hopefully it'll sink in. So I'm going to change the width of shape 1. That would give me a neutral axis exactly where my other neutral axis was. So here's my two shapes now. Oh, I tried to make it the same, in essence, the same size as what I had before. So this is still my E2. E2 hasn't changed, but up on my top shape, I'm going to change this so now it is equivalent to an E2. So now we do have the same modulus of elasticity throughout, and I end up with a neutral axis exactly where I had it a little bit ago. And if I did that, then looking at my stress and strain, my strain actually looks exactly like it did a second ago. But now the difference is my stress also looks exactly like my strain profile. There's no discontinuity anymore because in essence I'm treating it as if it has the same E value. So let's talk a little bit about how to do this. I have the derivation shown in the notes, but because YouTube I don't have very much time, I'm not going to do that derivation. But in essence, what we're doing is we're sticking with, in this case I changed the top E1 into a different size. I changed the size. So I still have B2. It looks just like it did before. Up on top though, which we called B1 previously, because it's slightly different, I'm going to call that B1 prime. It's a new width. We'll talk about how to find that width in a second. This is still my H1 and H2. The heights didn't change during this whole process. Like I said, I have the derivation in the notes, which we're going to skip because YouTube doesn't want me to upload big videos. Instead, I'm just going to give you the equation. So this is going to look like this. My new width will be equal to my original width times the ratio of my moduluses, or maybe moduli, of elasticity. But what does that actually mean? So we're going to have some names here. We are going to define a new term. We're going to define a modular ratio. As the name indicates, a modular ratio is a ratio between the different moduluses of elasticity, and I have E1 over E2. Something like that there. Now, when you're doing these problems, you have to keep straight which modulus you are doing, which one you're putting over the other one. When I have this E1 and E2 thing, the top number is what I got, and the bottom modulus is what I want. In other words, if I'm transforming shape 1 into shape 2, which is what I did here, I'm starting with E1, I'm dividing by E2. Try not to flip those things. If that's true, then going back to my transformed width, I now have an equation that says my B1 prime, my new width of the material that I changed, is equal to the modular ratio times my original width. So here's the basic process that you should be following when you're solving these problems. The first step that you're going to do is you're going to transform your different sections into a single width. You might have more than two materials, but in our case up above where we just showed one material, I'm only changing one. But overall, I have to transform into one material, or in other words, what I really need to do is create these B1 primes by multiplying times the modular ratio and the original width. After I do that, as you can see up above, I end up with a non-symmetric section. Because I have a non-symmetric section, I'm going to go back and, just like we did with non-symmetric sections with bending stresses, I need to find my centroid, which is the same thing as my neutral axis, and I also have to find the moment of inertia about that centroid or that neutral axis. After I find out that y value, then what I can do is plug it in and find my stresses. And the way I'm going to find my stresses is similar to what I did before with these shapes, where I would have a sigma. Now I do have the potential to have a sigma prime, and what the prime indicates is that that's my transformed area. So this is all based on the fact that this is a transformed, maybe you'd want to call it a transformed stress. I don't know if people do that, but you could keep it straight that way. It means it's not the actual stress, because the stress would be dependent on the cross-sectional area, and that's not the actual area we have. So the last step would be to transform it back in order to find the actual stress on the materials. And the way I transform it back is my stress will be equal to my modular ratio times this transformed stress. I'm just multiplying that n by that previous stress. So once again, during this process, if you have not transformed your section, like say on this upper one, if I were doing this process and I wanted to know the maximum bending stress at I don't know, maybe A and B, and I was looking at those two pieces, for A, down here, I would not do this last little bit because I never transformed that area. For B, I would have to do step 4 where I actually transform it back out. So you're only doing it for the ones you're transforming. You can also just build it straight into your stress equation by putting your modular ratio in there when you're solving it. Meaning you can say that sigma of your transformed area is just equal to n, which is your modular ratio, so that'd be equal to E1 over E2 times your stress, which would be minus my over I. I suppose you could develop one master equation like that. You could keep it in steps, whatever works out best for you. To keep this video from being too long, I am going to do a separate video that actually has an example of this process. But I hope that was helpful, and thanks for watching. See ya.